Hey everyone, welcome to ALevel Mechanics with Daniel Dallas. This is a revision and I consider vertical motion under the force of gravity. It's all about basically point particles, different objects that you can consider as point mass, right? The mass is concentrated as in the point, and so that any rotational effects can be neglected, so we consider only translational motion. All right, and we gonna go through harder questions, EP and P level, also challenging questions. All right, so here is a quick reminder from previous videos where I discuss all three main formulas that you can use and that's very applicable to in order to cope with this sort of problems for the vertical motion topics. Okay, and if you're not sure why each formula looks like, you can see right now on the screen, so check out my previous video. And also if you're wondering about physics that lies behind the scene, it's also gonna be useful to watch. All right, so bear in mind all those formula. Here is the problem one. Okay, EP level. Just read carefully, grab your pens, grab your notes, and try to do by your own as always. Okay, so what's happening here? Particle P is run vertically upwards from point O with speed u meter second to the negative 1, so means it is the same as if you use the index rule, right? You just flip over and you'll get meters per second. So meters per second, that's an equivalent way of writing. Okay, so 2 seconds later it still was moving upwards with a speed equals to a quarter of u. Okay, find the value of u. So what scenario we have in the first A part? So actually we have the following. We have point O. It might be the point somewhere on the ground, on the surface, or it might be any point in the air. It doesn't matter. So in this case, we can say that initial velocity was directed upwards, and the speed, it means the absolute value, was u. Okay, somewhere after 2 seconds passed, okay, it reached this point, for example, and here it had velocity quarter of u. Okay, so that's why I put small vector here and I mark this as 1/4 of u right now, and still upwards, right? It was moving upwards according to the words. So we need to figure out the value of u to 2 decimal places. All right, so let's do this. So what we're gonna do, we're going to apply the formula that expresses the final velocity through the original one, okay? And due to the fact that gravity force and hence acceleration directed downwards, so we can say that it's going to be u minus gt. Okay, so instead of v as the final velocity and final value of the speed, we can use the quarter of u according to initial statement. So that means right now if we plug this into the formula, we'll get u minus gt. All right, so we given the time, which is 2 seconds. We have g equals to 10, so from here we can recalculate u. So first of all, express u, so transfer to let's split the variables. Gt, actually it's not, the variable is known in this case, but u we can combine with u on the right side, and it's going to be 3/4 of u will be equal to gt, from where we can express that u finally is going to be 4 gt over 3. If you're really confused about re-expressing or formula rearrangements, so I encourage you to calculate immediately, just plug all the values in, and that will be much easier for you. But for those who want to struggle or who wants to get the final expression and only then plug the values, here is the final expression so you can reconcile. All right, and here we going to plug 4 times 10 times 2 is going to be 80 here on the very top, and over 3. That's going to be the value of velocity. So it's around 26 point. Yes, actually, let's calculate quick. So 80 over 3, 26.67 meter per second. Okay, so that's scenario, and that's basically the picture that you can have for question A. So find the time interval from the instant P leaves O to the instant it returns to O back again. All right, how it looks like? Let's put drawings first of all. Let's say here is the point O. It starts from here with initial velocity as we defined before. Okay, that's going to be initial velocity that we found, and after reaching the maximum height where velocity is 0 or speed is 0, it goes backwards. Obviously, due to the fact there is no air resistance, it comes back again to point O with the same velocity, but directed downwards. So that means you can say in terms of vector velocity is going to be negative u, obviously, but the value is going to be the same. If you're not sure, you can derive this fact by your own, okay? But I'll use this fact. So, which formula to use in order to find time interval? Of course, I think there is no way to use, let me see. Actually, there is the way to use formula for final speed, yes. So final speed is going to be equal minus u because downwards, right? As you remember, we stick to the rule that we direct, let's say, y-axis or x-axis, doesn't matter. So, and we project everything on that axis. And we can use initial velocity, which is positive, and minus gt according to, of course, according to the rule. From where you can establish time, so you'll get 2u equals gt, from where time traveled to the maximum height and the way back is going to be equal to u over g. Okay, here is an alternative way using displacement, okay? So this is way 1, which is pretty straightforward, but I'll show you way 2 because it's always applicable here. So I can consider the total displacement, okay? Let's consider total displacement. It's obviously 0 because it goes upward and the way back. And total displacement, as you remember, displacement is a vector connecting the starting point and the ending point, is going to be 0. And according to the formula, it's going to be equal to ut minus gt squared over 2. Okay, so hence you need to solve this equation that ut minus gt squared over 2 equals to 0. So you can factorize t, and in the brackets you'll get u minus dt over 2. Okay, and because the result is 0, there are two options. T1 is going to be equal to 0. That's the starting instance of time or moment of time. So T1 equals 0 is basically when it starts moving upwards, okay? And from the second brackets can be also equal to 0. So that means the second time instance is going to be equal to u over g. And if you compare with the way 1, you'll get the same, absolutely the same expression, okay? So that's why, as you can see here, you can use several ways. If you don't know which way to use, just try to put several equations by just step by step. For example, you wrote this, you understand that you can find this, can find time, so just don't do anything except for solving this equation. If it's not possible, try to write down another equation. It might be helpful, okay? And I just, in many cases, I encourage to write several equations in order, if you don't know what to do from the very beginning. Just try to express, let's say, final velocity, try to express displacement, and see what you can do here, okay? Is it possible to find it, or it's not possible? So, okay, and let's calculate time. Finally, time is going to be equal to u over g. And if you plug the values, so just times 2 and over 10, we'll get 5.33 recurring. So to 2 decimal place, that's going to be eligible answer. All right. Okay, so well done. That's the value for the speed to 2 decimal place, and this is the value for time travel to the maximum height, max height, and the way back. Okay, hope you got it. Let's move to the next problem. So, well, the problem is not really complicated if you start considering it and maybe in a systematic way. So just let's see what's happening. So here is initial height, right? Point in part A. So here is initial height, and we input x-axis, let it be x-axis, and here's gonna be the ground, okay? Here is gonna be the ground surface. All right, so it starts releasing, and it's released from rest, means initial velocity 0, but anyway, it's released from the rest position, which is at height of 12 meters. Okay, and it goes down before it collides with the surface. It hits the surface, then the speed is lost. So you need to find the height above the surface reached by the ball when its first time rebounds off the surface. So that means its initial height, and after rebounds, it will lift up, but not to the same surface. Not to the same height. Let it be height h1 that this ball reached after rebounding. Obviously, you need to know their initial speed during the rebounds, okay? This u1 is the speed after losing 10%, okay? So that means it's 0.9 or 90% out of the speed that it has before, right before a collision after falling from the height of 12. So that's going to be 0.9 times v. And in order to find u1, okay, first of all, because obviously from there we can calculate the height 1, which is simply u1t minus gt squared over 2, or maybe it's easier to use another formula, because in this case you need to know the time, so that's why it's better to use this formula, which is u squared over 2g. Both use minus sign, so I'll cancel them, because the final velocity at this point is gonna be 0, so that's sort of v at the point in time when it reaches h1, okay? I just put h1, and this velocity and the speed itself is 0, okay? Because this is the maximum height that reach up to the bounce. So we can calculate using this formula, and u1, actually I just need to correct a little bit. So u1 is the initial speed after the first bounce. Okay, so that's why first we need to find this v, and when it's possible, we can find the final h1. All right, so let's calculate v just right before the collision. So maybe it's better to mark the points like 1. If I input indices, it won't be useful. All right. Anyway, so v at this point is gonna be calculated as, because we're given height, yes. So we can use the formula for v through the height. So h is equal to v squared over 2g. Okay. Because again, initial velocity here is 0. So at this point, it's 0. So that's why we just left with that one. We can calculate v as square root of 2gh. And so we're going to use g equals 10. So we can just plug in and write, so 20 times height, which is 12. and that means we can calculate straight away. All right, so let's use calculator, and it's going to be 20 times 12 and the square root of that. So I've got around 15.5 to 1 decimal place. We're not stated, so that's why I'll give the answer to 1 decimal place. Let it be 15.5 meter per second. All right, so we've got this value. It's right here, and that means u1 we can also calculate because it's 0.9 from that. So we just times by 0.9. It's going to be 13.9 meter per second. That's going to be u1. So from here we can calculate the height 1, which is u1 squared over 2g. So it's going to be 13.9 squared over 20. And right now we can calculate this with no doubt. All right, so we just raise up into square and divide it by 20. So I've got 9.72 meters. If you're if you stay at 10% decrease in speed, so it's going to be 10% basically decrease in height. So it means you just can't subtract 1.2 as 10%. It wouldn't be correct, right? Because look, right now we can estimate h1 to the initial height, which is actually 972 to 12. And if you calculate that, just divide simply by 12, I've got around 0.81. So it means that the ratio represents 0.81, so that means more than 10% loss in height, okay, during the bounce off. All right, hope you understand that speed 10% decrease, 10% lost of the speed is not equal 10% lost or loss in height. Okay, make sure you understand this. Okay, so second time it rebounds the surface. Now what we can do, we can apply the same approach, and simply we can just say that u1 squared becomes u2. Okay, so that's going to be now u2 squared over 2g. Okay, and now we need to understand what's u2 in terms of u1. Okay, we've calculated u1 as 13.9, and I'll just maybe draw the picture a little bit here, small picture, which means that right now it bounced off the second time. So that was initial height, that was second, that was the first bounce off, and here is going to be the new one, which obviously smaller, okay, and this is the surface ground. So initial speed when it bounced off is going to be u2, which is going to be again 0.9 from u1, right? That's the fact, because when it bounced off with u1, it reached back with u1 again. Okay, that's this principle of symmetry, because the starting speed becomes the final speed when it goes from h1 back to the surface again. So that means it approached with the u1 that was originally during the release, okay, after the first bounce. And obviously u2 is going to be 0.9 of u1, so I hope you got it. 0.9 of u1 squared over 2g. That's going to be the result. So right now we can calculate this. We've calculated 17.9, so we've got this. 0.9 times 13.9, which is going to be squared and over 20. Why I marked h1 is obviously it's going to be h2, okay? It's going to be h2, sorry. Because this is the height after the second bounce. So it's going to be h2 equals, and let's quickly calculate 13.9, which is going to be squared everything, and over 20. So what I've got 7.83, so 7.8, okay? 7.8, that's going to be the second height after second rebounds. All right, so hope you got it. Hope you got it. It wasn't really confusing. And we'll move to more challenging problem that's actually challenge. Because right now we are going to consider particles interaction when several particles released from different points and they meet at one single point. Here is the challenging problem 1. It's all about interaction particles in the way they collide and one single point after some time passed. Alright, so try to read carefully this problem. Try, as always, try to do by your own, and let's have a look how it can be solved. But before we're doing that, obviously we need to change a little bit our equation for the displacement, and I'll show you soon why. Okay, so first of all, let's have a look at the picture. So let it be the ground level. So the ground level, let it be here. So this is the ground. And here is the point O, where the particle P starts its motion. It starts its launch with the speed of 35 meter per second. And I can mark like this. So that's going to be for point P. So that's why we can mark up initial velocity as 35 meter per second and goes up. Alright, so after 1 second, obviously the second particle Q has been launched vertically upwards from the same point. So that's why I just depict the case, and we can state that point or particle P somewhere here, and of course it has some just another velocity. Let this velocity be Vp at this time. We don't know which velocity, but we know that time passed is going to be 1 second. So it's going to be 1 sec. And at this time, a new particle has been launched with greater velocity. So it's going to be a particle Q. So that's why initial velocity for particle Q is going to be 50 meter per second. So obviously the speed is going to be greater in order to meet particle P somewhere in there. And after some time, let's assume that I mark as red. Here's going to be the point where both particle meets, somewhere here. So they goes upward and just the way back. So that's why after just coming back, particle P and particle Q meet each other. All right, so that's the point where they meet. How to solve this problem? Of course, first of all, we need to input x-axis and let it be in this way, because when we're talking about the point where both particles meet each other, obviously it's going to be a single point, and displacement formula is not really applicable. So we need to transform displacement formula in order to calculate the time when time passed from a moment where both particles launch. I'll show you 2 ways how to do that, and the first way is pretty easier to go. But before, as I promised, we need to understand how to transform equations in order to find that. Alright, so as you understand, for particle P and for particle Q, we have different time periods when those particles are in the air from the very initial moment of start. So that's why we can say that if for particle Q time from before collision, I mean the time starting from the launching instant and up to the meeting instant is going to be t. For particle P is going to be t plus 1 second, all right? So because it 1 second early start moving. So that's why t plus 1 is the travel time. Okay, so that's why we need to transform in order to describe the position where 2 particles meet each other. So let it be position x, and as you remember, so we do have the formula that tells us about displacement. So displacement is going to be ut plus at squared over 2. And even if you write according to what you have, instead of a, we do have acceleration g. Anyway, it tells you about displacement, so the vector that connects initial point and up to the starting point. All right, in our case, because we can set up our initial point here at the ground, and that's going to be a 0 point, and on the x-axis, displacement basically now point to the coordinates, to the point which would coordinate x. So that's why instead of displacement, we actually have the coordinates, right? The coordinates. But just keep in mind that displacement is always the final coordinate minus initial one. And just in case, if I'm just going to go through the second way how to solve this problem, and I'll show you how to transform this formula so that it actually reflects the coordinate instead of their vector of displacement. Okay, so I hope you understand that in our case, x0 simply becomes 0 because initial coordinates start off from 0 position, okay? From point O, where x equals to 0. So that's why instead of displacement, we directly have x. All right, so now what we're going to do, I'm just going to write for point P and for point Q this formula with respect to basically initial parameters. So the final coordinates where particle P meet particle Q is going to be x, and the right side is going to be the following. So initial speed t, up times t, and as you understand, it's positive, right? So our initial velocity is directed in the same way as x-axis, so that's why it's positive. However, acceleration, because it goes downward or directed downward, has a negative sign, so it's going to be minus gt squared over t. All right, so what about time? As you understand, you need to plug t plus 1 in this formula, so that's why instead of t, we need to put t plus 1. So, and let's do it right now. So we've got t plus 1 here and minus gt plus 1 squared over t. So here we go, we have the formula according to the time t plus 1. What about position when particle Q meets particle P? So that's going to be described using the same formula, but where initial velocity is for particle Q. So that's why we write in UQ. Travel time is t for it, and that's why we'll get simply minus gt squared over 2. And as you understand, coordinates are equal to each other, so that's why you equate. So that's position for P, that's position for Q, and they are equal. So that's why you can equate the left side and the right side of those equations. So that's why we also plug parameters, as we had 35 and 50, and also we're gonna use g equals t, all right? Sorry, g equals 10, yeah. It's too late for now. All right, let's get to it. So you've got 35 times t plus 1, so that's why I expand the bracket, 35t plus 35, and g over 2 is going to be 10 over 2, so we'll get 5. So, all right, 5. And here is t plus 1 squared, so I'll just expand the brackets. So t squared plus 2t and plus 1 finally. And that's going to be equivalent to what you have for Q. For Q, you have initial velocity 50t, and again minus 5t squared as a result of canceling. Now we understand that if we start expanding brackets, we will cancel those terms because they are the same. So finally, what we have here is going to be the following: 35t, let's just expand the brackets quickly. So it's going to be 35t next plus 35, then we continue expanding, minus 10t minus 5, right? And on the right side, we have only 50t. From where 35t and 10t and also 50t will give you somewhere around, I guess, 25t and is going to be equal to 35 minus 5, so it's going to be 30. From where t is going to be equivalent to 30 over 25, which will give you 1.2 seconds. Okay, but this is not the final answer because we need to calculate the time between instant when particle P is launched. So from very beginning. So to this answer, we need to add those 1 second because that's the total travel time, okay, up to the moment of collision. So that's why the total travel time is going to be 1.2 plus 1 second. It turns out to be 2.2 seconds. Okay, to two significant figures, that's what we did, even without rounding. All right, so hope you got this part, and let's move to the second part. So we need to calculate displacement from point O to the point where PQ collides. So basically displacement, I mark this as green bold vector. It's going to be from here up to the point with the coordinates x. So that's going to be the final displacement, and I put s here. And this vector is going to be positive. So because remember that displacement is always the vector, but we need to make a projection on x-axis. So as on x-axis still positive, and what we can do, we can use this total time. Why not? And in this case, we need to apply parameters for P. So total time for P is going to be T equals 2.2 seconds. Okay. So that's why if we plug into the formula ut plus at squared, we will get, so up times total travel time minus gt squared over 2. That's always the case. And right now we're just going to calculate by plugging this parameter and also initial speed. Okay, so let's do it quick. So what we've got 35 times 2.2, okay, and minus g over 2 is going to be 5, so minus 5 times 2.2 squared. Okay, now let's go back to calculator machine and do it quickly. Minus 5 times 2.2, which is squared. Okay, so what I've got 52.8. So the total displacement is going to be 52.8. All right, in this case, meters, that's the units. So that's going to be the answer for part B. And as I promised, I also try to explain you what if you like start thinking differently, because like many students actually, sorry, my bad, many students actually start thinking about, okay, why not to maybe approach in a bit different way. Okay, so one more time, the way to, if you start thinking in that way, let's assume that you decided to first take into account the first part of the motion. When particle P is probably somewhere here, it has some VP velocity, and from this moment you start thinking about how to calculate basically you start consider situation from this moment of time when particle P traveled 1 second, so 1 second after, and it's your like starting positions. No problem, you can start considering situation from here. So that's why you'll get the following picture. You got a point Q, you have the point P, so you have like sort of initial velocity. So that's going to be initial velocity for first consideration, mark probably as star, UP as star, because it's not going to be 35, right? You need to calculate this velocity. And for point Q still gonna be this value, which is 50. Okay, that's your starting point in your consideration, and after that you understand that the time until both particles meet at some point is going to be somewhere here. So let it be midpoint. Okay, midpoint, and you probably particle P goes upward and then goes down to this point. Okay, and particle q just goes straightly up, and they meet here. Okay, that's the case what you have. Like, many students start thinking from this moment, and I want to tell you that this approach is a bit harder because it takes more calculations and takes more evaluations. All right, anyway, I'll show you, because other students are confused about why we start considering from very initial point of view, okay, from the very initial moment when particle P is launched. Let's consider, well, 1 second after. It doesn't matter. It's not a big deal, except for maybe a bit more complexity. All right, so first of all, let's calculate VP after 1 second, okay, from 1 second, 1 second after. And according to the formula, it's going to be your initial P, right, minus GT, okay? So where T is 1 second, so that's why we just plug the values. It's going to be 35 minus G 10 times 1 sec. So if you calculate, you'll get 25, and that's going to be initial velocity. All right, so next point. For the next point, we can state that from using this velocity, we can probably again apply the both formulas for their position. So for point P and point Q. Now, travel time is going to be the same because 1 second has been passed, and now at this time, the second particle has been launched, okay? So that's why travel time is going to be T, and we apply the same formula for x coordinates. However, hold on, because here is going to be displacement from this point up to the median point. And you understand that initial coordinates for P, for particle P, is going to be some point x0 that we need also to calculate, because displacement is going to be final minus initial, okay, for point P. And according to consideration, is going to be, again, Vp, right, this velocity times time, and minus gt squared over 2. As you notice, because velocity, in our case, 25 meter per second, and it's positive, right? So we apply the positive sign. We project, it means at this point of time, or at this time instance, it's still upward. So that's why if we input, of course, we forgot to input x-axis, as in previous case, it's going to be upward. So as you understand, because the projection is positive, it still goes upward, okay? Because otherwise, maybe if at 2 seconds after, maybe let's say 1.5, probably it might change direction. So be careful about this moment. Okay, that's why this approach is a bit harder if you take into consideration. All right, so let's move next. And for point Q, we still have initial position here at 0. So that's why minus initial position will get the same x coordinates, and original velocity for Q, T, and still minus gt squared over 2. All right, now we need to calculate x0. So according to x0, we just need to plug into the formula 1 seconds, okay? And we calculate using the same structure, but instead of VP, we're going to use UP. All right, so let's do it. So UP was 35, so we got 35 here, times time, 1 second, and minus 5, it's going to be 30. All right, as you can see, we've got 30 here, and that's initial coordinates. Okay, so let's move next. So it's going to be 30, and we just plug into the formula, and we equate both x's. So what we have the following: 30 plus 25t, and minus g over 2 is going to be minus 5t squared. That's the left side when x expressed through it, okay? So next part, x here is going to be uq, so it's going to be 50t, and minus again 5t squared. So here you can cancel more easily, and we've got the same 30 and 50 and 25. So we got 30 equals 25t, from where t is again 1.2 seconds, but don't forget to add those time, 1 second as total time. To have total time, you need to add this, obviously. And we got the same answer. So maybe more complicated in terms of taking into consideration several formulas, but this approach also works. So I'll recommend to use approach 1, which is here. It's easier in terms of start thinking from very initial conditions, and what you need to calculate is just the coordinates, okay, where they meet, while here you need to go and over through several addition calculations. Obviously, to calculate displacement, you're gonna use the same way as are used here. All right, so that was challenging problem. Hope you got it, how to first transform as UVAT formula, right, in order to get the coordinates but not the displacement, okay? And the second step, to how to approach in general to this class of problem where two particles meet each other. So that was complete explanation. Hope you like that, and we're gonna move to the next problem soon. Don't forget to subscribe if you're new here, and share with anyone who's still struggling with A-level mechanics, year 1. Before you watch the solution, or probably if you're not start doing that, consider visiting my dance channel. It's all about dance. If you're an outdoor person, if you're sociable, so it's gonna be right for you guys. Check out the level there, check out the styles. That's gonna be a short trailer in a few seconds. Enjoy. So what we do have the ground level somewhere here, and that's gonna be the height of that cliff where both objects P and Q have been thrown. Okay, so we mark H as the height, and object P that has been thrown as the first object with initial velocity, which is 0 according to the words, right? And it passed some time, so some time has been passed, 1 second, because 1 second later another object Q has been thrown as well. So the time moment where 1 second has been passed, object P somewhere here, it has some new velocity Vp, but we don't care because we will consider from very starting point the whole motion of this object P. But what I'm gonna tell that object Q has been thrown, okay? And if we marked initial velocity for Q was 30, and if we mark the total travel time for Q as t, so let it be t is the total travel time, and travel time between instances when object Q has been thrown and both P and Q reach the ground, okay? So t is going to be travel time for Q. So object Q took less time in order to travel because it has greater velocity, larger velocity 30. The value is definitely larger in comparison with the initial for object P. So for object P, we will get t plus 3. That's going to be travel time for object P. It took 3 seconds more. Oh wait, why 3? Sorry, my bad. There's only 1 second. All right, so that's why we're gonna write t plus 1. I just recently solved another problem where there were 3 seconds. So it's gonna be t plus 1 second more for object P. Okay, so we set up time parameters, and now we can set up equations for P and Q. Let's start with object P and set up the formula. The distance traveled, in this case it's height, both objects traveled the same distance. And initial velocity for UP is going to be 0, but I'll write the general formula for that. And you understand why I'm going to use plus, all plus signs, because all both velocity UP and G accelerations, they projected positively along x direction, which is downward. So that's why if we rewrite this formula by plugging the parameter UP, which is 0, we'll get g over 2 t squared. So in our case, g over 2 will give us 5, and we'll get h equals 5 t squared. But hold on, t is the travel time for object P. In our case, it's t plus 1. So instead of writing like this, yeah, we can set up that it's going to be a travel time for object P. We put the indices here, and if we come back to what we've marked as t plus 1, that's actual travel time for object P. Whenever t stays here, tp stays here, we need to set up t plus 1, obviously. So finally, for object P, we'll get 5 times travel time t squared is going to be t plus 1 and everything squared. All right. What about object Q? The travel time is just t, so that's why we're going to use the straight formula with initial parameter 30. So we will write this. If you like, you can put indices which denote travel time for Q, but travel time for Q is actually t. And right now we're going to plug this in the formula. So 30, that's initial speed, times t, and plus 5t squared. That's what we'll have. So we'll get equation 1 and we'll get equation 2, and we want to combine them all. Now we have both values h and t, so we can resolve with respect to h because we need to find the height. But if maybe it's easier for now, if we find the travel time t, we will find height finally. So that's why, just because I have on both sides h, let's find first at travel time. So t as the first one. Of course, you know that you can express t from here, just plug in. So find t first. You can, express t through h and plug instead of t, but I'm not going to do. I'm just use a bit easier way, maybe a bit longer, but it's actually easier. So what I'm going to do, I'm just going to equate both equations 1 and 2, because I'm going to solve as simultaneous equation, and I'll get the following 5. Let's expand the brackets. T plus 1 squared is going to be t squared plus 2t and plus 1 in the brackets. What about the right side? The right side is going to be 30t and plus 5t squared. As you can see, it's a pretty cool equation. It's sort of quadratic one, but I hope it's going to be cancelled out to linear. 5t squared plus 10t and plus 5 will be equivalent to 30t and plus 5t squared. As you can see, both 5t squared will be cancelled. So that means you'll be left with 10t and 30t. So it's going to be 20t over here and 5 over there. So from there, we can find that travel time for object Q is going to be equal 5 over 20. 5 over 20, or 1/4 of 0.25 in decimal seconds. So 0.25 seconds. And what we're going to do, we're going to plug to find h. So for example, for simplicity, I will use equation 1 and just calculate straight away. 5 times t plus 1 squared is going to be 125 and squared. Now we can calculate this fast and quickly. Alright, 5 times 125, which is squared, and I'll get around 7.8 to one decimal place. So 7.8 meters, that's the height of this cliff, and that's going to be final answer. As you can see, if you're supposed to find also travel time, for example, for object P or for object Q, you already have this. So that's travel time for Q, and with no doubt, by adding 1, you can find travel time for object P. That's not actually the problem. On top of that, we can expand this problem and we can calculate, for example, their velocity just before the fall, right? Just before touching the ground. That's, for example, for object Q, it's pretty easy to show that final velocity for Q is going to be initial velocity UQ and plus GT. Alright, because we know the time, which is 0.25 seconds, so we can easily calculate VQ with no problem. And you can do the same for object P with no doubt. Alright, hope you got it. I'll show you also expansion, possible expansion. Basically, this is a variation for problem 2, so make sure you understand every single step. It's all based on pretty simple formulas, and actually for now it shouldn't be a challenge for you guys. I hope you got it. Alright, and don't forget to visit my dance channel. I hope you find something for you. See you next time.